All right. Hello. Good morning. Good evening. Good afternoon. Let's look at the exercises, the warm up exercises for 2.4 here. For the first one, you've got to review the buy two, get one free theorem, which looks just like this. And the key thing for both A and B is that if A is a square matrix, that means the columns form a list of C vectors in R to the power C, and we also know the dimension of R to the power C is C. For example, the standard basis vectors form a basis with C vectors in it, so that makes RC have dimension C. So yeah, give these a shot, and the answers will appear in 3, 2, 1, and here they are. The first two are true, parts A and B, because what the buy two get one free theorem says is that you have a list with the right number of vectors in it, meaning if your vectors are v1 through vn, and so the number of vectors you have is equal to the dimension of your subspace, so in this case C equals C, then you just need to know one of the two parts of what makes a basis to be true for the other part to also be true. So the first one says you have the right number of vectors equal to the dimension of RC, and it says for every y in RC, the equation ax equals y has a solution. That means that the columns a1 through ac of A span RC. So that makes part 3 of the theorem true, and the buy two get one free theorem says that makes the other thing automatically true. Likewise for A, this is saying they're linearly independent, and there you have two of the things for the buy one get one. You have two of the things for the buy two get one free theorem, the right number of vectors, and they're linearly independent, so the third thing is true as well. Now, if A is not necessarily square, then neither of these are true because you don't know that the number of vectors is equal to the dimension of RC. So yeah, it might be a good exercise to come up with a counterexample of these. If you can come up with a non-square matrix that makes parts A and B false, that would be a good exercise. But let's look at exercise 2. When you multiply E and F using the row column rule, you get the identity, and doing it the other way around also gives you the identity. And we can also see that the row operation that transforms I into E is the inverse of the operation that transforms E back to I. So every row operation has another row operation that can undo it. Okay, so we will look into a lot more detail in the next video about elementary matrices, which E and F here are examples of. So I will see you then.